will be explaining my Lab 5 for Physics 2211, which is the falling slinky. So an introduction to the lab, the purpose is to analyze and determine the motion of the bottom of a slinky when it's dropped and how it is affected by drag force. The procedure starts by comparing two different position versus time graphs, one from Tracker, which is our experimental, and one from GlowScript, which is our computational. And the principles of physics used are Newton's second law, weight force, and drag force. So my project choice was the slinky. The system was just the slinky itself, and the surroundings are earth and drag or air resistance. The initial conditions are the slinky is dropped from a man's hand, so the initial velocity is going to be 0. And the main result of this experiment is that we can predict the motion of the bottom of a slinky using forces of gravity and drag until the top of the stretched slinky reaches the bottom of the slinky, or it's no longer being stretched. There's no more tension in the slinky. The net force is going to be 0, and the bottom of the slinky does not move. After the two ends meet, they fall together due to the force of gravity and encounter drag force opposing their motion. We can predict the motion of the bottom of the slinky by using net force equations for gravity and drag, and then using that to set the velocity and position. So in my data from Tracker, I got the mass of the slinky being 0.204 kilograms. That was from the video. The initial position, the final position, simply by tracking the slinky on Tracker, the initial velocity is 0, and the final velocity I calculated by using all the data points for the position. So I got the average velocity. Okay, my initial code. So I used the mass from the video. I did the position and velocity from Tracker data, and I did the delta t from Tracker data, and I found the drag coefficient by trial and error to mimic the Tracker data graph. So I just did trial and error until I got it. So in my first while loop, I set the time constraint to 7.2 seconds, which was the time that the bottom of the slinky stayed in the same position or had a net force of 0. Also the time that the slinky was stretched. Then I calculated the force of gravity, which is mass times gravity in the y direction, the force of tension, which is just simply the same magnitude as gravity but in the opposite direction, and then the net force, which is both those added together, but it's going to give you 0 because they have the same magnitude in opposite direction. I did velocity and position update formulas as well. Okay, then in my second while loop, I got the average velocity of the slinky's fall from Tracker. I set that initial velocity equal to it before the second while loop. Then I got the total amount of time measured after the first loop, which was 7.2 seconds, until 10.0 seconds, which is the amount of time that the slinky actually fell, like the bottom of the slinky. I calculated the force of gravity, then I calculated the drag force using the speed to calculate the drag force in the y direction. So we're going to have the force of gravity and the drag force in the y direction. The drag force is going to oppose the force of gravity. And then I did the net forces, both of those added together. And then we got the velocity and position update formulas. So my experimental versus computational models gave us this graph on Excel. The computational model lined up somewhat accurately to the experimental model. The first part is very accurate because the slinky was stationary, so it was easy to model. But the other possible sources of error for where it went downhill, which is when it started to fall, was human error, possibly tracking the slinky on Tracker, or human error creating the code. The drag coefficient was created by trial and error, so that's never going to be exactly perfect. Or maybe there was a calibration error when I was measuring it on Tracker. So post-experiment questions, does the bottom of your model slinky stay stationary just like in the video? Yes, the bottom of my model slinky stays stationary because I created code to make sure that it would. In my first while loop, the net force is 0, so the bottom of the slinky does not move. And in my second while loop, the slinky starts moving with the force of gravity and drag force opposing it, but the second while loop doesn't start until the time in the video where the slinky started moving. This is because I modeled the computational model after the video and after my Tracker data. So the bottom of the slinky stays stationary until the slinky is not being stretched because of the force of tension. The forces acting on the bottom of the slinky are gravity and tension, and they are equal in magnitude and opposite in direction, which causes the net force on the bottom of the slinky to be 0. So in conclusion, the bottom of the slinky stays stationary until tension force equals 0, or when it is no longer being stretched. And we can model this motion in a computational model with the force of gravity, tension, and drag force.